Some of the most important rules with differentiation are the linearity rules. So the derivative of a sum is the sum of derivatives, and the derivative of a multiple is the multiple of the derivative. Well, it's kind of natural for us to say, well, are there similar results for antiderivatives, right? Is the antiderivative of a sum the sum of antiderivatives, etc.? And the answer is absolutely. And you can really, in a very loose way, understand that by thinking the definition of an antiderivative is related to a derivative, so all the same rules should work. Now, we're just going to remind ourselves about this notation. Remember that when we say we have a function, it's related to its antiderivative in the two different ways. The switcheroo way, where the function, the antiderivative, is by itself, or the differential form, where it's differentiated and connected like this. So we're just going to use this notation here and show very easily that, yes, we can get the same linearity rules. So if we were to take this expression here, let's take a look at that. F of x plus or minus g of x, according to the notation that we've got here, this would just be f prime of x, f prime of the antiderivative, plus or minus g prime of the antiderivative. Now, these are derivatives. So that means I get to use the linearity rules. And here I get to use them in reverse. So it'll be f of x plus or minus g of x all prime. That's the linearity rule in reverse. And that's really all there is to it. Now I'd use a switcheroo. I'm going to switcheroo this to the other side, and I will end up with the following result. This is f of x plus or minus g of x. And if we use the notation that we're looking for, you can see that exactly the result we expected to pop out pops out. That the antiderivative of a sum or a difference is the sum or difference of the antiderivatives. Very, very easy, very expected, and it's kind of reassuring that it does work out that way and exactly that way that we're looking for. Now, similarly, if we are interested in the antiderivative of a multiple just like this, we can start the same way. If we take our function, we know that it's related to this, so taking a multiple of it is like taking a multiple of the derivative, and this is where we get to use the linearity rule in reverse. This is just c times f of x all differentiated, and that's the key. If I switcheroo now, I will have that the antiderivative is equal to c times big F of x, and this is where my result pops out, that the antiderivative of a multiple is c times the antiderivative itself. So I can effectively pull out the constant, and we get the two results we were expecting. And now this is all great. We can combine all of these results and use them just like we would in any other example. So for instance, if I say, hey, now we can get a lot of mileage out of the power rule, the product rule, or sorry, all the basic antiderivatives that we need. And it just allows us to kind of write things down like this. So this is one big ugly problem, and like when we learned about differentiation, there's no need for us to write it as one big ugly problem and tackle it as one big ugly problem. We're going to tackle it as several little easy problems, and that's what linearity lets us do. The antiderivative of a sum or difference is the sum or difference of antiderivatives. So I get to split this apart and write it like this. The antiderivative of a multiple is the multiple of antiderivatives. And so I get to write it like this. I get to take out all of those constants. And finally, if I want to take this, I need to rewrite them so that they are all in the form that the power rule can handle. And it's a minor change, minor rewrite, but what I've done is taken one giant antiderivative problem that was challenging and written it as 3 smaller antiderivative problems. Now we're going to introduce some notation here. If I were to use the power rule on each of these, I would get the following. Add the power by 1, put it upstairs and downstairs. -5 plus 1 is going to be x to the -4 over -4 plus c2. And now 4/3 plus 1 is going to be 7/3 over 7/3 plus c3. Now you'll notice that each one of these terms gives you an arbitrary constant. So what I'm going to do is I'm going to group together all the terms with x's, and everything else I'll group together in a moment. Now remember, -6 over -4 gives me a +6 over 4. This other term is going to give me a -15 over 7, x to the 7/3. And now, 7 times an arbitrary constant minus 6 times the second constant minus 5 times the third. Here's a wonderful little trick. An arbitrary constant plus some other arbitrary constant plus yet another one. All of this is just going to give me some arbitrary constant. So we don't ever bother. We just group them all together at the end. You don't even need to bother with the intermediate ones. We'll just write it as one single constant the whole way through, and we never waste our time with trying to write them separately and then recombine them at the end. It's just no point to doing it. Now, finally, we can talk about what we were interested in initially. In a Newton's second law problem, we would like to find f of x if the second derivative is provided for us, if the acceleration is given to us. So, for example, we might be given something like this: 4 minus 6x minus 40x cubed, and f of 0 is equal to 2, f prime of 0 is equal to 1. So this is going to end up giving us a 2-stage antidifferentiation. Now note, since the derivative of f prime is f double prime, that means when we switcheroo it, f prime of x is the antiderivative of f double prime of x. So that means f prime of x, we are going to have to antidifferentiate this function, 4 minus 6x minus 40x cubed. And so when we antidifferentiate that, we can use linearity, and we split this up into as many separate integrals as we need, antiderivatives as we need. So we'll get a 4 times x minus 6x squared over 2 by the power rule, 40x to the 4 over 4, plus the constant gets grouped together at the end. We don't need to bother with the constant along the way. We can clean everything up here. Now we're going to apply one of the initial conditions, that f prime of 0 is equal to 1. We are now at the stage where we have a formula for f prime, so we're going to use it. So we'll get 4 times 0 minus 3 times 0 squared minus 10 times 0 to the 4 plus a constant equals 1. And that obviously tells us that our constant is 1. Similarly, f of x is going to be the antiderivative of f prime of x. And that tells us that we're going to take the answer we just got for f prime, and we need to include the 1. That 1 is important. It helps set the problem so that it satisfies the conditions we need. This is going to give us yet another round of linearity. We're going to antidifferentiate everything we need in the way we need it. So this will give us 4x squared over 2, x cubed over 3, x to the 5 over 5, x, and now we're going to get a new arbitrary constant. So we'll get a 2x squared, x cubed, 2x to the 5 plus x plus some d. The initial condition is f of 0 equals 2. So if I apply that initial condition, I'll get exactly what I need. So this is going to give me 2 times 0 squared minus 0 cubed minus 2, 0 to the 5 plus 0 plus d is 2. And so clearly d is equal to 2. And once I put this all together, I've got exactly what I need. I have now found the one and only one function that tells us the solution to the problem. Now finally, we can kind of sum it all up. Derivatives and antiderivatives are inverse operations. What do I mean by that? According to the definition of an antiderivative, you should get this. And if we use our proper notation here, what we're going to find is this. The derivative applied to an antiderivative, they just go away. You get back the function you started with. So a derivative will undo an antiderivative. So a derivative undoes an antiderivative. Now at the same time, if we kind of take a look at the other direction here, right? The derivative of a function is f prime. So if we switcheroo this, f of x is equal to the antiderivative of this. And what we're seeing is that the antiderivative of a derivative just gets you back the original function. So the antiderivative undoes a derivative. It all makes sense. Plus sign, minus sign, multiplication, division, differentiation, antidifferentiation. Everything makes sense.